case people wander in late, they don't have to. Okay, so I am going to talk about a triangle that governs the infrared sector of all physical theories with massless particles. And there are three corners of this triangle. One is the so-called soft theorems, which started, I think, in 1958 with Francis Lowe, or you could even go back to Bloch and Nordzig 20 years before that. And they're a statement about Feynman diagrams, properties of Feynman diagrams and scattering amplitudes. Then there's a seemingly separate subject of asymptotic symmetries or conservation laws, which is the same thing as conservation laws by Nether's theorem. And I kind of dislike this word asymptotic symmetries because it suggests that they're somehow not exact, that they're only true in some asymptotic sense. But asymptotic symmetries are symmetries just like any other symmetry. And the reason they're called asymptotic symmetries is that they typically take a simple and recognizable form when you look at how they act on the asymptotic regions of space-time. But they are not approximate symmetries. They're exact symmetries that, just like other ones that we might have studied. And then there's something called the memory effect, which exists in many different forms. Mostly investigated in the context of gravitational physics. And all three of these topics have histories, hundreds or even thousands of, certainly in the case of this one, thousands of papers. And they've all been studied for half a century, but they are separate lines of investigation with people using different notations and different languages that didn't talk to one another. And what we've learned in the last several years is that these three subjects are really the same subject, and the same ideas were being developed in parallel in different languages. And the connections between them, these were, the connection here is a ward identity. Whenever you have a symmetry, you have what's called ward identities, which are consequences for scattering processes of the symmetry. This one is the simplest of all. It's simply a Fourier transform in time. The names were really just different because they were ideas that evolved in different communities, and they called them different things. And then here we have something which are just vacuum transitions. Now, this triangle, it has many copies. It echoes throughout much of physics. And for example, we could be talking about, and we will talk about, QED, Yang-Mills theory, that is non-abelian gauge theory, gravity. But it is also now becoming evident that versions of this triangle appear even without theories with local symmetries like the three that I've written here. for example, just theories with massless scalars, any theory with massless particles, scalars or fermions. Now, on the soft theorem side, there are so-called leading soft theorems. Soft theorems, the word soft means zero or low energy, and a soft theorem is a theorem about some behavior of an amplitude at zero or low energy. And there's a chair here. Maybe you could move over one. And so you have leading infrared behavior of amplitudes, but you also have the subleading behavior. And then you have the subleading behavior. And in fact, there have been suggestions that this triangle could continue on to arbitrary subleading orders. There's a classical story, which is what we'll start out with. Already there's a fully classical version of this story. And then there's a quantum version, and where one will encounter, in general, an interesting story involving anomalies. We started out the discussion in four-dimensional Minkowski space, but we could also take d less than 4 or at d greater than 4, and we could also look in the case of cosmology where there are also soft theorems and associated symmetries. Finally, you could take supersymmetry. We start at n equals 0, but go all the way up to 4 or 8. Actually, I guess we could go to 8. So now, for every one of the combined possibilities here, each story, the surprising thing of the kind of richness of this subject is that each story has its own unique and interesting features, and they need to be worked out one by one. So if you look at all the possibilities here, subleading, QED, classical, if you look at all the possibilities here, there's of order 500 possibilities, each of which will require a paper, and maybe 30 of these papers have so far been written. So this is a subject which is in its infancy, which I think makes it a lot of fun to talk about. Now, why is this interesting? What is the motivation? What is the motivation in applications? So the first thing is that it's always a good idea to connect. These are all three of these subjects, soft theorems, memory effects, and symmetries, which are different ways of describing the behavior of the universe around us at very long distances. And one of the things I think we're going to see at this course, is that the behavior of physics at very long distances is really, though people understood it in a way, we're going to see that it's really much richer and more subtle, and certainly much less understood than we previously believed. So we connect three different subjects, and that's always a good thing to do, because you can take a result in the study of soft theorems and turn it into a result in the study of symmetries. And often, in fact, I think there was no case prior to 3 years ago in which all 3 corners of the triangle were understood. But now that we know about this triangle, we find one corner, we can work out the other 2. So in all of these subjects, there are many things that we can learn by applying this universal triangular relationship. So, and these are 3 subjects on each of which has its own vast literature. Now, the second motivation, which is how I came into the subject, maybe not how I go out of it, but is I wanted to understand the holographic structure of quantum gravity in Minkowski space, in 4-dimensional Minkowski space. So there's been a beautiful story which has been very intensely developed over the last, I guess, almost 20 years now, about a holographic structure of quantum gravity in anti-de Sitter space. And that story began with the identification of the symmetries in anti-de Sitter space and in its holographic dual. And so the very first question we should ask if we want to understand something about quantum gravity, some purported or sought after holographic interpretation of quantum gravity in 4-dimensional Minkowski space, which ought to be the most interesting case, is to understand what the symmetries are. And amazingly enough, people didn't know the answer to the question, and before 2 years ago, they didn't know the answer to the question of what are the symmetries of quantum gravity in Minkowski space. And not only did people not know it, they knew that they didn't know it. And now we know a lot more about it. We've understood something about BMS and super translations, but we also know that there are still more pieces of it that we have yet to understand. We know that at the very least there's an infinite dimensional symmetry group, but we don't know if we have the whole infinite dimensional symmetry group now. So the sort of 0th order question that you would ask in trying to understand whether there's a holographic formulation of quantum gravity in 4-dimensional Minkowski space has not been answered, but I think we have the tools in hand that we can use to try to answer this question. Now, the third thing is the study of soft particles in quantum field theory, in LHC events, in the study of jet structure, the study of the infrared structure of the S matrix in QED, in Yang-Mills theory. That is a huge subject, which is certainly one of the, if not the central subject in trying to understand quantum field theory, and also in trying, in a very practical sense, trying to interpret signals that we observe at the LHC. Now, one of the things that we are going to see in this course is that the soft physics in the standard model in quantum electrodynamics and in non-abelian gauge theory is governed by an infinite dimensional symmetry group. So this many decades, going back to the 50s and 60s, of research on LHC, and there's one of the leaders in the study of soft physics peering in the window. He just disappeared. is you know, to understand this soft structure, and we now have realized that it's controlled by a symmetry, an infinite dimensional symmetry. And surely to understand and properly formulate this problem, we need to invoke these symmetries. So all of this work has been done without direct knowledge of the symmetries, and some people have expressed the hope that these symmetries can actually lead to more effective computations of LHC scattering amplitude. So organization, improvement, of IR, jet, LHC physics. And related is simply the question, which has never achieved a satisfactory answer: what is the S matrix in QED or the standard model? I'll have you, one of the readings will be chapter 13 in Weinberg's textbook, and you will see there that that there is no there is something that there is no definition of the S matrix in the standard model or in QED because of the problem of infrared divergence. So one might hope that that the knowledge of these symmetries will enable us to formulate that in a better way. Now, I didn't start this project with this in mind or with this in mind either, but it turns out that this whole story has important implications for the black hole information problem, because that is also a problem having to do with the deeper infrared, because much of the radiation that comes out, in fact, there are an infinite number of soft gravitons and soft photons that are produced in the process of black hole evaporation, and one needs to understand both the conservation laws that govern them and the nature of the information that is carried in them. And finally, this is more related to 3, is there's something called the amplitude program in n equals 4 Yang-Mills. And what has happened in the n equals 4 Yang-Mills story, the very active subject, which has been going on for about 10 years, is that they do a lot of computation and they find a lot of very extensive computations, many by brute force, and they find all kinds of amazing cancellations, and at the end of the day, they get very simple expressions. And there is not within that program any explanation of why the answer should be so simple. Now, when you have a lot of cancellations, the natural thing to suspect is that things are canceling because there's a symmetry which forces them to be equal, and therefore they have to cancel. So I think that this picture I'm developing could possibly, they refer to these cancellations as miracles, but I think that this picture I'm developing could possibly give an explanation of those miracles, and even better, a derivation of some of the incredibly simple and beautiful formulas that they've derived for scattering amplitudes in n equals 4 Yang-Mills theory. Now, of course, I'm going to talk both about the connections, which are the new things, but at the same time, I'm going to be reviewing the three things at the corner. So the course will be a mixture of some very old stuff and some very new stuff. All right. So that is kind of the end of the section which I've entitled BS in my notes here. and now I'm about to actually start to write down some equations. But are there any questions about the BS before I get on to the equations? Okay. So we're gonna start. It's a kind of odd subject that in trying to present this, you could have. It's an interconnection between many different things. So there's a question of where you start, whether I start with gauge theory or with gravity, with soft theorems or with symmetries. And so there are many different ways to present this. But I think I'm going to start in sort of the simplest context, which is I'm going to start with back in the 19th century with some basic equations of electromagnetism. So electromagnetism can be described by an action. And unlike in most courses that I teach, I'm actually going to try to get all the factors and everything right. That I may find that challenging, but I'm going to try. Okay. So we start with an action. And the reason for that, it's so much fun to see these things being exactly equal, even though they're written in such different ways. So we start with a Maxwell action, Maxwell field strength squared. And the comments I'm going to make will be Maxwell theory. For now, everything is classical. Be Maxwell theory coupled to any kind of matter. So I'll just denote it generically as matter. And here A and B are running from 0 to 3. And F, the field strength F, in form notation, which I'm assuming you know, is equal to dA. And we can write the equation of motion as d star F equals E squared star J, where J is the variation of S with respect to A. Now, notice I've got a 1 over E squared in here, which means that my covariant, I'm using conventions in which the matter action doesn't have any explicit factors of the coupling E in it. So the coordinate covariant derivatives will just be D minus A, not D minus EA. And this implies, in non-form notation, dA/FAB is equal to E squared JB. And now I'm going to define an electric charge, Q electric, by 1 over E squared, the integral over 2 sphere of star F. And of course, we can take that 2 sphere, we can integrate by parts, and we can write that as 1 over E squared integral D star F over some 3 volume whose boundary is that. But from this equation here, this becomes just integral over sigma of star j. So that's just saying in form notation that, so if we took sigma to be a time-like slice at t equals 0, this would just be the normal component of j integrated over that slice. And now, this q is not quite the q you're used to. I'm defining my conventions so that in the quantum theory, this q will be an integer, with no factor of. So this would, if we had an electron here, the electron would have charge 1 instead of charge e, and that's because I put a 1 over e squared here, not a 1 over e, and that's just going to make my life easier later on. Now, there's another kind of charge that we could discuss here, and the other kind of charge that we could discuss would be a magnetic charge, which would also have a conservation law, and that would be the integral of f. And there would be a similar formula here if we had magnetic charges along. But I'm doing one thing at a time. And so for now, we'll come back to the magnetic charge case, which turns out to be very interesting. But for now, we're just going to assume there are no magnetic charges around. Now, this theory is, of course, gauge invariant under delta A is equal to delta epsilon A is equal to d epsilon. And with epsilon, doing a U1 theory, epsilon goes to epsilon is periodically identified, epsilon plus 2 pi. And if we have some field of charge k, delta epsilon phi k, will be equal to I epsilon qk phi k, where qk is an integer, so that if I take the finite transformation here, I'll get an e to the I epsilon qk phi k. And so in order for this to be invariant under epsilon goes to epsilon plus 2 pi, qk has to be an integer. And also the magnetic charges with this identification would also be the integral, I think 1 over 2 pi, the integral of f will also be an integer. Okay. Now I want to consider something very simple. I want to solve this now. This is I'm doing still in 19th century electromagnetism. And let me just pause to ask if there are any questions about my notation. Or yeah.
The very last exponential on the last line, but that's the e to the I epsilon.
QK. It's this QK. So phi k is a field with charge QK. QK is an integer. This is just my conventions. And so the thing that forces it to be an integer, of course, classically, electric charge is not quantized. But quantum mechanically, a wave function for a particle created by the field phi k should be single valued under this. Okay, so now I want to take consider a source J, which corresponds to some number of particles, I don't care how many, which are moving with velocities. So we have k particles, and they have velocities uak, which I'm going to write as gamma k times 1 beta k. So u squared is equal to 1. Gamma k squared is equal to 1 over 1 minus beta squared. This is the standard Lorentz factor.
The level A is leveling the different particles?
No, the K is I should have made a thing like this. So K labels the different particles. A is going from 0, 1, 2, 3. So UK0 is gamma K, and then the other three components are this vector beta K. So whenever I put a vector here, I mean a three-dimensional spatial vector. So beta would be beta 1, beta 2, beta 3. Okay. Now, so let me write so JA of x, I'm going to take as the sum over m particles, k equals 1 to m, of qk, the charge of the kth particle, times, so we'll give it a world line parameterized by x of tau. So delta fourth xa, so this is JA of x, which is equal to qk delta fourth xb minus ubk tau times uak. Okay, so this is just tau is a parameter along the, so it's a point source. Tau is a parameter along, a constant parameter along the world line of the particle. This thing is 0 unless xb is equal to the 4 velocity times tau for some tau. And when that happens, it's a delta function. So there's a delta function at every point along the world line. So now you can try to solve this equation with that source. And Lienert and Wiechert did this in 1898. And I won't go through it. So this is just m particles in constant motion. And the answer for the radial component of the electric field is that FRT is equal to E squared over 4 pi times this sum, where k equals 1 to m, of, now it's a little bit complicated, qk. So we get a sum of contributions, one for each particle. It's qk gamma k r, where that's the radius. So r, I'm going to define r squared equals 3 vector x dot 3 vector x. Minus t x hat. So I'm going to define x hat as a unit vector so that x is equal to r x hat. It's a unit vector pointing in the direction of the particle, r minus t x hat dot beta k. So this term basically depends on the angle. So the angle between, so this is FRT of evaluated at x and t. So it depends on the angle between the velocity of the particle and your position, divided by gamma k squared t minus r x hat dot beta k squared minus t squared plus r squared all to the 3/2 power. Okay, so this formula was derived in 1898. Now, we've all seen this formula before. We've probably also all suppressed it, or at least I have. And I did not realize until a few years ago, really only a year ago, that this formula has a very peculiar property. And the peculiar property is that its value at r equals infinity is that it is not single valued at r equals infinity. In fact, it's discontinuous at r equals infinity. This came as kind of a surprise to me, though I'm sure many people knew it. But this is going to be crucial. This fact is going to sort of be the bedrock of everything we do from here on. So I'm going to go through it in pedantic detail how this happens. Okay, so yes, I haven't lectured in this room for a while, and there's a trick to how you pull the blackboards up and down. Okay. So if we want to talk about infinity, and indeed which we do, we're going to be talking a lot about infinity in this course, it's important to write things in terms of Penrose diagrams. So here's the Penrose diagram for four-dimensional Minkowski space. It looks like this. And lines of constant r this would be r equals 0. Lines of constant r look like this. And this line out here is r equals infinity, r equals infinity, r equals infinity. Now, Penrose, so this is a picture in which one has collapsed all of Minkowski space into a finite picture, and also lines of constant t. So notice that lines of constant r all end up at this point, and then lines of constant t look like this, the yellow ones. Now, sometimes there's a little ambiguity here. Sometimes the picture would be drawn differently. I'm not going to do this, but let me just do it and then erase it. Sometimes we would say, okay, this is r equals 0. This is r equals infinity. This is r equals infinity. Every point on here is a two-sphere, except for r equals 0, which is an origin. So if you have a sequence of two spheres that are getting smaller and smaller, and then you add a point in the middle, that gives you an R3, right? That's R3, a sequence of smaller and smaller two spheres with a point in the middle. Okay, here, each point is actually a hemisphere. So, but somehow especially with this antipodal business, I find this kind of picture more useful. So this, if we got here, we're sort of going at the North Pole or somewhere in the northern hemisphere out to infinity. And then if we go in the opposite direction, we go into the South Pole. Okay, so now I don't want to try to draw all m of them, but we want to study the electric field of charges, let's call them electrons, moving at constant velocity, and they would have a world line that looks like this. So they can't get out to here, so light rays are going at 45 degrees on this picture, and every light ray will eventually catch up to a particle moving with constant velocity and cross it to larger radius. So the electrons always have to end up at this point up here, which is called future time-like infinity. Similarly, this point down here is called past time-like infinity. And while I'm labeling things, this is past null infinity. This is future null infinity, the place where light rays go, the place where light rays come from. Now, we're very worried about what goes on here. And it turns out that this place out here, which is sometimes called spatial infinity, or the point spatial infinity, it turns out to be very subtle, and almost anything, even Maxwell electromagnetism with one point particle, is singular at that point. And so we have to distinguish here between, Scri plus is a two-sphere times a null line. And so if we want to talk about, we have to separately distinguish between the past of Scri plus, which I call Scri plus minus, and the future of Scri minus, which I'll call Scri minus plus. These things have to be carefully kept track of. And we also have down here Scri minus minus, which is a two-sphere, which is different than I minus, which is a point. And also up here, we have Scri plus plus. OK, so the claim is that if we take this rather innocuous-looking Lienard-Vicard potential, we also want to talk about when you do scattering in Minkowski space, the problem that you want to solve, whether it's quantum electrodynamics or quantum gravity, you want to start with some initial data at past null infinity and possibly I minus, and you want to evolve it to future. You want to solve some. So when you go into the past past, the far past, everything disperses, everything becomes weakly interacting. So in general, we're going to start in the far past, and the scattering problem, which is the topic of this course, or much of the topic of this course, is suppose you have some classical initial data, such as some incoming waves, or some incoming quantum state. It's weakly, everything is weak in the far past because things tend to disperse. But then these things can come in, interact in some very complicated way, and come out on Scri plus. So the scattering problem, classical or quantum, is finding either a classical map from a point on the phase space described in Scri minus to a point, or a classical map from the phase space on Scri minus to the phase space on defined on Scri plus, or in the quantum world, it's finding the S matrix, which involves incoming states defined on scry minus to outgoing states defined on scry plus. Okay. So, but now clearly in that studying that, what goes on here is very important, because we have to know, given our initial data here, what exactly we say about the beginning of the initial data for scry plus minus. We need to understand what the boundary conditions are, which relates the fields at scry minus plus to scry plus minus. And what you might have thought is that they're simply taken to be equal. That turns out to be wrong. It's not, in fact, it turns out not to even be a Lorentz invariant condition. And it's also not true in this very simple example. Now, so in describing scry minus, it's useful to introduce something called advance time, which is V equals T plus R. So V equals T plus R is the advance time, and then we have the retarded time up here, which is U equals T minus R. So coordinates, good coordinates, we can't use T. So scry minus is a three-dimensional surface. We can't use 4 coordinates. We can't have T. We might try, for example, to use T, R, and X hat being a direction which picks out a point on the sphere. We might try to use T, R, and X hat. But that's awkward because T and R are both infinite. But if we follow null rays backwards, T plus R is finite. And if we follow them forwards, T minus R is finite. So scry plus is naturally coordinatized by T and X hat. Sorry, by U and X hat. And scry minus is naturally parametrized by V and X hat. Okay, so now here's the weird property of that potential. If I take this start at some finite point and I go up to scry plus and then back down to scry plus minus, I get a different answer than if I go down to scry minus and up to scry minus plus. Okay, so let me do that. But let me also introduce these coordinate systems, which I'm going to be using. So we're going to have retarded coordinates. Which we want to use in a neighborhood of scry plus. Which would be ds squared is minus 2 du dr minus du squared plus 2r squared gamma z bar I think I'm going to, write this on a different blackboard. All right, so we have ds squared. Here's retarded coordinates. ds squared is minus du squared minus 2 du dr plus 2 r squared gamma z bar dz bar. Now, what have I done here? Well, u is this retarded coordinate. R is the radial coordinate. And if we keep R fixed and we keep u fixed and take R to infinity, we go out along a null line like this. And how can you see that that's a null line? Well, if du is 0 and dz is 0, z is going to be a coordinate on the sphere, then this whole thing is 0. So ds squared will be 0 for lines of fixed u, z, z bar, and varying r. And this, the standard metric on Minkowski skip space would be ds squared equals minus dt squared plus dx dot dx. And that's related to this one by, first of all, by r squared equals x squared. U equals t minus r. And then what is it? It's then there's the question of what z is. And z is given by x1 plus I x2 equals 2rz over 1 plus zz bar. And finally, this gamma zz bar is equal to 2 over 1 plus zz bar squared. So we're going to be using this kind of metric a lot in this course. It will simplify things. Let me just explain a few things about it. So this is the standard round metric for a sphere of unit radius, where z runs over the entire complex plane. Z equals 0 would be like the North Pole, and z equals infinity would be the South Pole. This funny 2 is here because, well, we would have gamma zz bar plus gamma z bar z. Naturally, we would have two terms that look like this, but we've just added them up and multiplied by 2. This is a z, not a 2. OK. That's the definition of these coordinates. The equator is, I think, at zz bar equal to 1. OK. And of course, we could write formulas exchanging z and z bar for theta and phi, but this ends up being more convenient for a lot of reasons. Now, this is a good thing to do near Scri plus, because as we'll see, everything falls off near Scri plus, and we can start expanding fields in powers of 1 over r near Scri plus. But we couldn't do that with these coordinates if we wanted to be near Scri minus. So we introduce an alternate set of coordinates, which is ds squared equals minus dv squared is minus dv squared minus 2 dv dr, sorry, plus 2 dv dr plus 2 r squared gamma zz bar dz dz bar. I'm going to write it a little bit differently. I'm going to write this as x hat 1 plus I x hat 2. And I'm also going to use the formula from over there, which is that x is equal to r x hat. And now I'm going to have gamma z bar equals the same. I'm going to have r squared equals the same. So I'm still going to have r squared equals x squared. But now I'm going to do two things different. I'm going to write v equals t plus r. And I'm going to write x equals minus r x hat. Now, this might seem like a crazy thing to do at this point, but it's going to make a lot of the formulas simple later on. So that means that the z in these coordinates is, and I'm still going to use this same formula. So that means that the z in the advanced coordinates is at the antipodal point to the sphere. See, taking x hat to minus x hat takes 1 point on the sphere to the antipodal point. So the z in this coordinates denotes the antipodal point to the z in this coordinate. So if I go back up to this picture, if this point were at z equals 0, then this point would be at the antipodal point, which would be, well, the antipodal map is z goes to minus 1 over z bar. So if this point were z equals 0, this would be z equals infinity. No, sorry, this would be z equals infinity. And if we take a light ray which crosses Minkowski space, like this, then the value of z that it starts with in advanced coordinates, in retarded coordinates, sorry, this value of z that it starts with in advanced coordinates is the same as the value of z that it ends with in retarded coordinates. Okay, now I might have, again, there are notational choices here. I might have called this w here and then said that w is just minus 1 over z bar, but that again, would introduce its own notational complexities. Okay. So now I'm all set to take this and okay, I promised a 5-minute break on the hour. So let's take our 5-minute break, and then what I'm going to do when we come back is I'm going to take this Lienard-Wiechert potential, which I've written over there. I'm going to rewrite it in terms of the advanced U, or V, and keep V fixed and take R to infinity, which will take me down to scry minus, and then go up to scry minus plus, and compare that to what I get if I go the other way. It's going to be a very simple exercise, and we're going to see that we get something surprisingly different. All right, let's take 5 minutes. Okay. So now I'm just going to do the special case of m equals 1, so we can drop all the k indices. And you'll see that it works how it works term by term. So we just need to plug in FRT is equal to E squared Q over 4 pi. And then we have gamma is a gamma factor. And then we have R. But now we want to study it. Let's say we want to study it at near scribe plus. So we should write near scribe plus. We should write T is equal to R plus U. So we have R minus R plus U x hat dot beta divided by, and I hope everybody is checking me, gamma squared, and then we have R plus U minus R x hat dot beta squared minus T squared, minus U plus R squared plus R squared to the 3/2. Okay, so now what we want to do, if we want to go to scribe plus, what does it mean to go to scribe plus? Well, it means we keep U fixed and take R to infinity. Okay, so that's why if we were to have left it in terms of T, it would have been awkward to see what it means to go up to scribe plus. That's why we rewrote it in terms of the retarded coordinates. So if we take R to infinity, we can forget about various terms. So we get E squared Q over 4 pi. And at the top, we still have this gamma. And we can neglect the terms that are don't have an R in it. So we get an R times 1 minus x hat dot beta. And what happens on the bottom? Well, there we only need to, the highest power is R squared. There are things that go like R squared. And here we have U plus R squared minus U plus, so these terms can be ignored. And we only have to worry about this term. And this term goes like gamma squared. And again, we can drop this. R squared 1 minus x hat dot beta squared. And this is all to the 3/2. And so now we see that we get E squared Q over 4 pi. And this is all going to go like, well, let's do the gamma first. We have a gamma on, well, let's write the top. Gamma R, wait, we can do this. Let's look at the gammas. So we have a gamma on the top and a gamma squared to the 3/2 on the bottom. So that's a gamma cubed. So there's a 1 over gamma squared here. Similarly, there's a same power of R. So we have a 1 over R squared. And then we would get a 1 minus x hat dot beta cubed on the bottom. But that's, again, canceled by the 1 minus. So this is it. 1 minus x hat dot beta squared. Okay, so that is the answer. That is the behavior of the FRT, which is really the electric field, at large R. Now notice that if we take beta to be 0, this just becomes 1. And gamma becomes 1. And this is 1 over 4 pi r squared with the weird factor of e squared q just coming from my conventions for q and the electromagnetic field. There's a lot of chairs in here if you, yeah. Maybe somebody can squish over one. Okay, now let's do the same thing. Now, one other thing I want to mention here is that the leading 1 over r squared component of the electric field, when you have moving charges, is not a constant. In Jackson and all those textbooks, we spend a lot of time talking about static configurations. So for a static electric field, the 1 over r squared thing is just proportional to the electric charge. And then the dipole moment, the 1 over r squared term for a static field comes from the dipole moment. Here there's no dipole in the picture. We just have one charge. But there is a dipole moment. The electric field at infinity is not constant. It depends on the angle of the sphere at infinity. And that's an intuition that we have to, the dipole moment of this is not what would usually be called the dipole moment in classical electromagnetic textbooks. Okay, so now let's do the other thing, which is, so actually, we went up to scri plus, but there was no u dependence here. So we can immediately go back down to scri plus minus. That's just because we're considering such a simple problem. Okay, now let's do the other situation where instead of substituting in t equals u plus r, we substitute in this formula t equals v minus r. So you probably immediately see what's going to happen. Everywhere we have a t, namely here, well, let me do it. So then we get FRT is equal to by the way, FRT, if we do the coordinate transformation, FRT is the same thing as FRU. And FRT, which is the same thing as FRV, becomes equal to, again, Q gamma E squared over 4 pi. But now look what happens. Now we have R minus V minus R times x hat dot beta here, and divided by gamma squared times V minus R minus r x hat dot beta squared minus v minus r squared plus r squared, all to the 3/2. So you can see what happens now, that now when we go to large R, we neglect this term here. But because it's a minus sign, 2 minuses is a plus. So it's just like we did before, except we lose those minus signs. So this becomes equal to, for r goes to infinity, it's equal to e squared q over 4 pi gamma squared r squared 1 plus x hat dot beta squared. So these things are not the same. So even for the case of one moving charge in Minkowski space, the radial component of the electric field is not continuous at spatial infinity. Its value depends very much on how you approach spatial infinity. And it's discontinuous there. It takes definite values. If you specify a way of approaching it, going down from scry plus or up from scry minus, you'll get a definite answer, but it won't be the same. Now, notice, however, that, and by the way, this is a Lorentz invariant expression. In fact, the expression was gotten by boosting the Coulomb's law for a static charge. So this discontinuity is dictated by Lorentz invariant. And indeed, Lorentz transformations themselves are not smooth near spatial infinity, because while you're boosting away, if you write the vector field that generates the Lorentz transformation, you're boosting away from a point on scry minus, but if you're boosting away towards the North Pole in the future, you're going away from the North Pole as you go to the past. So the Lorentz transformations themselves are singular at that point. Okay, so now, even though they're not equal, notice that they are equal. They're antipodally equal. In other words, if I take x hat to minus x hat, I take this formula to that one. So, so in fact, and we even conclude for a arbitrary number of particles that we have the condition that FRU, the leading component, the limit as r goes to infinity of FRU, of r squared FRU, that's to kill the 1 over r squared there, of x hat, the point at which we're going to, at scry plus minus, is equal to the limit as r goes to infinity of r squared FRV of minus x hat on scry minus plus. So weirdly, the value of the field, and this would be true for a collection of m charges, the value of this so for a collection of m particles, you get a much more complicated formula involving a sum of its terms, but the terms will individually obey this condition, so that the value of the radial electric field at any point on scry plus minus will be equal to the value of the field at the antipodal point on scry minus plus. Okay, so this is a weird statement. Okay, now, I've just been doing a simple situation. It's not a static situation because the charges are moving, but nothing is interacting. So you can, I'm not going to go through this, but you can, one thing you could do is you could just add electromagnetic waves on top of this, and then we would no longer have constant epsilon here. But when you add electromagnetic waves, radiative modes, so these are all Coulombic type degrees of freedom of the electromagnetic field. If we add radiative modes and we want them to have a finite energy, they have to obey certain boundary conditions. They have to die off in the infinite future or the infinite past, otherwise the configuration will have infinite energy. So for finite energy configurations, adding radiative modes will give you much more complicated formulas that will depend on you up there, but they won't affect this basic behavior of the Coulombic part, the deep infrared part of the electromagnetic field, which is what we are studying here. So it turns out to be and one can study more complicated situations, and I'm not going to try to do that, but it turns out to be, well, this boundary condition is true in general, and then to state it in a better way, one of the things that we like to do is to expand. I'm going to introduce a little more notation now. So suppose we have a field, say the vector potential, the z component of the vector field, which depends on r, u, z, and z bar. We can write an expansion for that as a sum from n equals 0 to infinity as a z superscript n over r to the n, where these coefficients depend only on u, z, and z bar. Okay, so in general, we're going to be doing a lot of expanding about infinity. And I'm just introducing some notation here that, we will denote by a superscript n the order in the expansion, the power of r in the expansion about r equals infinity.
That's 1 over r to the n.
1 over r to the n, thank you. Okay, now, having introduced that notation, I can finally write the following formula, which is FRU2, that is the 1 over r squared term in the expansion of the RU component of the field strength around Scri plus at z bar evaluated at Scri plus minus. So in general, it would also depend on u, but, or I could also write this is equal to FRU2 minus infinity z bar, but I prefer this notation, is equal to F2 RV z bar at Scri minus plus. So now you finally see why I defined the z's as I did. So the z's at on Scri minus plus are antipodally related to the ones at Scri plus minus. And so I don't, here I had to put that minus sign in there. And this is going to simplify a lot of my subsequent formulas to have defined my coordinates in this way. So this is a very general boundary condition for classical electromagnetism, when our fields are not singular near spatial infinity. And we'll also see that Feynman later on, quite a few lectures later on, that Feynman diagrammatics implicitly assume this boundary condition in the standard weak field expansion in the I epsilon expression. And that might have been guessed from the fact just that these boundary conditions are Lorentz and PT invariant.
I have a question.
Yeah.
So here you only consider the leading order that would get this kind of condition. How about if we spin the higher orders and we have other conditions like R2, 5, or 4 order?
Okay, so this is a very interesting question. What I'm telling you about now, what about the higher orders? Yeah, very interesting question. What I'm telling you about now is there's so many different generalizations of this story that it's kind of hard to have one path through it. But what I'm telling you now is a story in this triangle that is ultimately going to take us to Weinberg's leading soft photon theorem. There is Lowe's subleading soft photon theorem, and we would learn about that. To learn about that, we would have to look at the subleading terms, and that is a story, and this I believe is also related to something that the Sket people call reparameterization variance of the jets in the Sket program. And so that's a very interesting story. A few things are understood about it, but and maybe we'll get to it later on. But for now we're just talking about the leading term. And there would also, of course, be an interesting story involving FZZ bar, the tangential, not the electric field, but the magnetic field. And that would be, again, we're suppressing that because we don't have any magnetic charge present at the moment. Okay, any more questions? I've written a lot of formulas on the board. Yeah.
How do we know how important this term is in relation to the size of the higher order term? And how quickly, for example, the series eventually converge?
Right. So interestingly enough, this question has been very rigorously studied in gravity. You know how the 1 over R expansion. This question has been very rigorously studied in gravity, and there's a treatise on it by Christodoulou and Kleinerman in the 90s. There was a lot of discussion about it by Penrose in collaboration, a lot of papers on it in the 60s, 70s, and 80s, which actually turned out to be wrong, and led to a lot of confusion in the community, and is part of the reason that the story that I'm able to tell now is made sense only in light of, seemed manifestly wrong before Christodoulou and Kleinerman. You have to worry about the behavior of these subleading terms, and you have to worry about how things behave as you get near scribe plus minus, even in electromagnetism, and especially in non-abelian gauge theory. Now, interestingly, the situation in non-abelian gauge theory is not as good as the situation in gravity as far as how much is understood. Why the mathematicians chose to nail gravity to death before. Christodoulou's students have been working on Yang-Mills theory, and there's some understanding of it, but not quite as well as gravity. But for the purposes of this, for the purposes of this course, we're assuming that things fall off in a reasonable way with a nice 1 over R expansion. And a lot of the statements have been rigorously proved for gravity, but less for electromagnetism. Yeah. Is there a first principle way to derive the matching condition? Well, I don't think there is any other matching condition that, my guess is probably yes, but I don't think it's been done. I've never seen this matching condition discussed. It's a property of the Liénard-Wiechert potential, and that's been sitting there for 130 years, 100 and whatever, 17 years. I haven't ever seen the statement that about this antipodal matching condition. It's true for every example that you can find. Now, I would guess there would be, and you can derive it quantum mechanically from the soft photon theorem. The soft photon theorem implies it, but it seems like pretty weird to be using quantum field theory to prove a result relevant to 19th century electromagnetism. Now, I'm sure that people in the late 19th century, early 20th century must have somehow known about this. I don't know, maybe they did. I don't know if they knew about it or not. But I would think that there would be some set of assumptions and some way to prove it and make it into a mathematical theorem, but I haven't seen that. The discussion of this mathing, I don't think it appeared in the literature. This formula appeared in the literature prior to, our paper a year or two ago. Yeah.
Can I just check that I understand that? So this condition means that you identify this F or U as R D as antipodal.
Yeah.
Because of the time.
Yeah.
So what would be wrong? I think there are some contradiction, some happening if you actually try to identify not antipodal type of just identify.
Well, you need an identification. You need what would go wrong? Well, you could certainly write, if you want to solve a scattering problem, you need you need to define what you're doing all the way out at infinity. So you need to know your starting point for integrating the constraints or whatever you're doing to get all your fields up here. I believe it would not be hard to prove that this is the only Lorentz invariant. Boundary condition, though I haven't tried to do it.
The antipodal matching is exclusive by this Lorentz invariant, or it has to be antipodal, because as you said, the Lorentz transformation acts differently.
That seems right, but I haven't said assume A, B, C, and then we've been more. There's so many interesting things that are true that as far as making rigorous mathematical proofs, that takes you know, that's mostly what we've been doing, but I think probably one could prove it. Now, I think if you have something which is very different from that, you could, of course, there's another way of thinking about this condition, which is familiar to, there's another way of thinking about this condition, especially in electromagnetism, which is conformally invariant. You can map it to the, you can map Minkowski space to the cylinder. And let me draw it like this. Here's the cylinder. And we have, here's the Minkowski diamond. Here's the cylinder where the cross sections are S3. And you can formally map Minkowski space to, I'm having a little trouble drawing this here. Why am I having so much trouble? Okay. Let me start over. Okay, let's take a point, which is spatial infinity, and we take the light cone of that point. So the future light cone of that point eventually goes around the cylinder and meets itself in the future, and the past light cone does the same thing. So this diamond, which we've seen the back of, here's the top and the bottom of the diamond. This diamond is wrapped on the cylinder and meets here. And so this antipodal matching condition says that the fields are constant. So what's null infinity? Null infinity, let me get a different color here. Null infinity is, future null infinity is this, and past null infinity is this. And the generators of null infinity go up like this. They go through spatial infinity from past null. This would be scribe minus, this would be scribe plus. And so this condition is looked at this way. This matching condition is saying that the fields are constant along the generators of null infinity, including when they cross. This is spatial infinity, which is a singular point. Now, when you do this kind of conformal compactification of Minkowski space to the singular, to S3 cross R, generically you have singularities here. I mean, even if you just have one charge, you would need to have an image charge here. So you can't demand that your fields all be smooth here. There's some, singularity there, and the natural way to define that singularity, which you can easily see as invariant under Lorentz transformations, which are just a part of the conformal group here, is to demand that it be constant along these null generators. And indeed, when we go to quantum gravity, which we will later on, it doesn't make a lot of sense to describe it by saying that the parameters take the same value at the beginning and the end of the light ray, because the space will be curved and the light rays will be funny things and there will be caustics and so on. But this way of phrasing the condition, that it is that the fields are constant along the generators of null infinity even as they cross at spatial infinity, is a very natural way of doing things. It surprised me a lot when I first realized it, but as you work with it, it seems more and more natural. Any more questions? Okay, great. So now we have this matching condition. And this matching condition immediately implies the existence of an infinite number of classically conserved charges. Because let me take any function epsilon, which I'm going to define so that epsilon zz bar at scri plus minus is equal to epsilon zz bar of scri minus plus. So I'm going to take a function epsilon which is not smooth near spatial infinity, but instead is antipodally identified. So we immediately get that if we define a charge q plus epsilon as 1 over e squared integral scri plus minus, the past of scri plus, epsilon star f is equal to q minus epsilon, which is equal to 1 over e squared integral of scri minus plus of epsilon star f. So this is an infinite number of conservation law in any theory involving electromagnetism, because there's one conservation law for every function epsilon. For example, in some uses, it's convenient to take these to be epsilons, the base of the epsilons to be the spherical harmonics, and then I would get one conservation law for every L and M. So it's one way of saying this conservation law is that the incoming multiple moments, the infinite number of incoming multiple moments, and in general all of them will be non-zero, of the electromagnetic field are equal to the antipodal moments. The antipodal map in that case will just give us a factor of minus to the L, because the antipodal map on YLM is just minus to the L, are equal to minus to the L, the outgoing multiple moments. Now, this is not to be confused. When I say multiple moments here, I mean multiple moments of the leading 1 over r squared term of the electric field. It's not like the dipole moment, which is the coefficient of the 1 over r cubed term or the whatever. I'm talking about just, okay. So this is infinitely many conservation laws associated with electromagnetic field. Now, these start to look more interesting when we write that, when we use the Gauss law to write the surface integral. Now remember that we can use Gauss's law, and we did it earlier on, to write the surface integral expression for the electric charge as a volume integral expression over the of the electric field as a volume integral expression of the matter charge currents. Now what happens if we do that? Well, let's write q plus epsilon. We can integrate by parts and write it as an integral over of 1 over e squared as an integral over scri plus d epsilon wedge star f So I'm just taking d of whatever is in there, plus integral over scribe plus of star j, and plus 1 over e squared, the integral over scribe plus plus, way up there, of star f, epsilon star f. Okay, because scribe plus has two boundaries. We have an integral over scribe plus minus, so we get a volume integral over scribe plus, and then an extra boundary term at scribe plus plus. So let me talk, and obviously for q minus, I get a similar expression. Q minus epsilon is 1 over e squared, integral over scribe minus, d epsilon wedge star f, plus integral over scribe minus star j, plus 1 over e squared scribe minus minus epsilon star f. So let me talk about these terms one at a time. The first thing is, in a theory with only, now over here I've been talking about massive charges. But now I'm going to do, we'll come back to massive charges later. But now I'm going to do something to kind of simplify the formulas. And then we'll come back and understand how we have to complicate them to get to what we want to describe. And the simplification I'm going to make at this point is that I'm going to assume that there are only massless particles present. So there can be massless, there are theories with massless charged particles. So I'm not assuming that there are no charged particles. But I'm just saying that if they are present, I'm going to assume that they're massless. Now, if you have a massless field, scribe plus is, so if you have a massless field, scribe plus, which is this surface here, there's a little hole in scribe plus at I plus. But for a massless field, you don't, the evolution, scribe plus is a Cauchy surface without adding in scribe I plus. In other words, we can get a complete set of modes. The initial value problem is completely well posed if we want to study, say, the electromagnetic field or a massless electron. The initial value problem is completely well posed. In quantum field theory, we get a complete set of modes if we just talk about what happens on scribe plus. Now, that doesn't work when you have massive fields. When you have massive fields, they go up, they die exponentially near, or actually they do really surprising, weird, counterintuitive things at null infinity. But anyway, you certainly must include I plus. And that doesn't mess up our story. In fact, it makes it more beautiful when you see how it all works out. But it certainly complicates the story. And also, if you have a black hole, which we'll talk about at the end of the course, you also have another a boundary term up there. But for now, we're divide and conquer. We're going to isolate the issues one at a time. And for now, we're going to ignore all issues associated with I plus, which means we're allowed to neglect these boundary terms. Now, let's suppose that there should have been an epsilon in here. Right. Yeah. I'm assuming that the fields are smooth and continuous up there. Okay, so now let's take the simplest case. Now, this formula is true for any epsilon obeying the condition I've written over there. But we're going to impose, we're not going to consider all epsilons. We could, but it would get us into a discussion which ultimately would not prove to be that interesting. We're going to take epsilon to be constant along scri plus and scri minus. I mean, our formulas are all true for this case, and we can, if we wish, we can talk later about what we would have learned if we had considered other kinds of. Somebody asked me later what would happen if we don't impose this condition. We can also talk about that. But for now, we're simply going to study what happens for epsilons that obey this condition, as well as the one in the square over there. Now, a particular case is just epsilon equals constant. It doesn't depend on the sphere. And if epsilon is equal to constant, let's just take it equal to 1, then this just becomes the sum of k equals 1 to m of the incoming charges qk. Let me write in here. And this becomes the sum of the incoming charges k equals m plus 1 to m plus, well, let me just write it, k equals 1 to n of q out sub k. So these two things are equal. This should look like a familiar statement. So for epsilon constant, the sum of all the incoming charges must be the sum of all the outgoing charges. Okay, but suppose epsilon is not constant. Well, I guess it's 530. So when epsilon is not constant, it's not a short story, but it's a good story to be thinking about for the next week. When epsilon is not constant, we're going to learn that there are, in classical electromagnetism, an infinite number of conserved charges which are on exactly the same footing as the usual conservation law, sum of incoming matter charges equal to sum of outgoing matter charges. Those charges are going to be kind of weight by angle the incoming matter electric charges, and they're going to have an additional mysterious term, which we're going to see is we could call a soft photon, which involves the electromagnetic field. So unlike the epsilon constant case, which is just a statement about the incoming matter configuration, this will involve the incoming electric field. But we will have an exact statement that relates various integrals weighted by epsilon of the incoming initial data to the outgoing initial data. Okay, so I guess we'll talk about that next time.